In this video, we are going to go over the steps to perform a robust design optimization with Sandia, Dakota, and MSC Nastran. Now, this example is going to require MSC Nastran 2023.3 or newer. There's a certain configuration in the bulk data file that requires a Nastran 2023.3 or newer. So just keep that in mind when you go through this exercise. Now, this is what we are aiming for in this exercise. Here, let's go ahead and focus on the left side of the screen. We have a response from a very simple finite element model. There's some variability in the inputs. The inputs are uncertain. So when we go ahead and run Nastran multiple times, we find out that the responses are also random. Here on the top left is the original distribution of that response. You can see the mean is around here. More importantly, the spread of the distribution is very wide, as an example. And now this is a problem for us. If we were to manufacture this actual model thousands or millions of times, the spread of the response, or here in this case happens to be the acoustic pressure or the sound in individual hears, will vary a lot. So you can imagine if we vary some of the thicknesses or the gauge thicknesses in the model, the sound the individual hears will vary by a lot, which is probably something we don't want. So in this exercise, what we want to do is we want to perform an optimization. We want to vary the thicknesses of the finite element model, and we want to reduce or minimize the spread. So here on the bottom left is the new spread after a robust design optimization. You can see that the probability density function, the spread of this PDF, is smaller than it was before. And we are going to do the same for a second response, R2. So here's the before and after of that response. If you look at the initial distribution of that response, is very wide. But when we employ a robust design optimization, we are going to go ahead and reduce the spread, if you will. So here on the bottom right, you can see that the new spread after optimization, it's a lot, or it's been reduced. Now, the way we are going to achieve this minimization in the spread, we are going to configure a objective function that goes as follows. We want to minimize the mean plus 3 standard deviations for response 1 and response 2. Now here on this slide is just a comparison of the exact values. If we go back to this slide, these two distributions assume that the thickness values are 0.02047, 0.02596. Here are the respective initial means and standard deviations. So here on the right is what the final new result looks like. We are going to have an optimal solution for the new means of the uncertain variables. More importantly, here are the new means and standard deviations. You'll see in a moment that not only did we reduce the mean, but we also reduce the standard deviation. Primarily, we want to reduce the standard deviation because the standard deviation influences how narrow the probability density functions are. Now, here on this slide is a problem statement for the uncertainty quantification part of the tutorial. Here, if you look at the model, it's an acoustic box. The exterior is composed of various walls that have a certain thickness. And then in the interior would be the acoustic mesh. We are interested in tracking or monitoring the acoustic pressure at these two nodes, node 11280 and node 11329. We have over, I believe, 10 thicknesses we can play with, but today we are only going to play with the thickness of P shell 4 and 5. Here on this table, you have some information regarding the distribution, which happens to be normal. log normal distributions, and we have the mean and standard deviation. Now, this configuration is the initial configuration. Later on in the optimization, we are going to vary the mean and find optimal means that reduce the standard deviations for the outputs. Here on the right is a quick summary of the responses. We want to track the peak acoustic pressure for one of the nodes, and then the second response would be the peak acoustic pressure for the second node. Now, R3 is going to be the mass or the weight of the acoustic box. I'll go into more detail what the constraint is later on. Now, some of the quantities of interest are the following. We want to know the mean and standard deviation for both responses. And for R3, the mass, we want to know the probability of exceeding the current or a desired mass of 2,910. This will be important later on in the optimization under uncertainty. Now, here is just a quick look at what the peak response looks like. We have a set of forcing frequencies, but we want to make sure that the peak response, we want to make sure that that distribution is small for the peak responses. Remember, if the peak response looks something like this, you can see that the spread is very wide. We want to narrow that distribution. So it may be something like this. So that's what we're aiming for. So we want to know what the distribution is for the peak response. And once we know what the distribution looks like, we want to narrow that peak response. So the way we're going to do that is as follows. If you look at the objective function here in the top right, the way we're going to reduce that distribution is as follows. We are going to minimize the sum of various components, if you will. We're going to minimize the mean plus 3 standard deviations for response R1. So that would be one of the peak acoustic pressures. And then we're going to reduce the mean plus 3 standard deviations for the second response. So response R1 and R2, remember, are the peak acoustic pressures at 2 different node locations in the finite element model. Now, for the design variables, we are just going to let the mean of the uncertain inputs vary. We're going to let the mean vary between 0.001 and 1. Now, what about our constraints? We want to make sure that the mass does not increase for the most part during this optimization. I think the mass is about, the initial mass rather, is around 2,800. And we want to make sure that statistically the mass doesn't exceed 2,910, at least 5% of the time. Now, said another way, we want to make sure that the probability that the mass exceeds 2,910, that probability is constrained to 5%. The probability of failure is 5%. Now, due to optimization tolerances, even though you constrain the probability of failure or PF to 5%, sometimes the optimizer will land on values of maybe 5.1 or 5.2. In certain cases, you might get something in excess of maybe 7 or 8% probability of failure. Now, this is expected. What we are going to do in this exercise, since we know the optimizer sometimes likes to land at slightly higher values, we're going to say use a probability of failure of 3%. So in the end, we might get a value like 3.1 or 3.2. In certain cases, we might get 4 or even 5%, which is okay. We know the optimizer will sometimes exceed the actual value, the actual upper bound. So we're purposely going back and saying, hey, use the lower probability of failure bound. In this case, we're using 3%. So I'm not going to go through every slide in detail. I'll leave it up to you to take time to print out a copy or view a copy of this tutorial and go through the slides thoroughly. I'll leave my email address here just in case you're new to optimization under uncertainty, robust design optimization. Today we're using Sandia Dakota. So if you're new to Sandia Dakota, you're more than welcome to contact me at this email address. Now, robust design optimization is a type of optimization under uncertainty. With robust design optimization, the optimization under uncertainty is using a very specific objective. So here, what we want to do is we want to reduce the spread of the distribution. We want to narrow the distribution. And the way we're doing that is with the subjective function, which is the sum of the mean plus 3 standard deviations. And you repeat this process for each response you want to reduce the spread for. Now, again, the reason we're doing this is because if we mass manufacture this acoustic box, every time we produce or manufacture this box, the thicknesses are going to vary some standard deviation. Now, the problem with that is when we look at the acoustic pressures from all million acoustic boxes that we manufactured, you'll see that the acoustic pressure is varying a little from box to box, and we want to control that variation of the acoustic pressures. So here on my desk, I have a physical printout of all of these slides with all of the steps. Feel free to get a copy of this presentation, this tutorial, and we're both basically going to follow every step in this document. So one of the first steps is downloading the bulk data files for this exercise. So here, let's go ahead and open the Sol 200 web app, and let's open the tutorial section, and let's navigate to the optimization under uncertainty tutorials, or OUU tutorials. Let's go ahead and find the tutorial row for this acoustic box, and let's download the starting PDF files. Now, one thing I like to do with the downloads directory, I always like to start off with a clean directory. I know that we download files all the time, and it's very easy for this directory to get a lot of files. Just to save ourselves the confusion, I cleared everything, and now we only have the files we're working with today. Now, the assumption is that you've already configured your acoustic box or finite element model. You have the nodes, the elements, the loads, constraints, and materials. You've already performed your modal frequency response analysis. You already have your subcases. Now, we did an extra step with these bulk data files. We configured this for Sol 200. Now, the reason we did that is because here, let me go ahead and run this one time. Let's go ahead and run Nastran for this set of bulk data files. With the simple modal frequency response analysis, you get, here, I don't know if it'll be available here, but we'll see. Oh, this won't work for this exercise, so I'll have to go ahead and run this with. So here what's going on is I'm using an older version of Nastran. So it's giving me an error that, hey, you're not using Nastran 2023.2 or 3. So here what I'm going to do, I'm going to pause the video and run this with my other desktop. Or actually, let's see if we can do this. Let me go ahead and use a tool here called the Remote Analysis Web App. And here, let me pause the video for a quick moment. Here, what I'm going to do is I'm going to open the web app that's running on a Linux server elsewhere on my network. So here you'll notice in the address, before we were using localhost, which is accessing the web app on this desktop, this Windows desktop. But right now, since I don't have the newer version of Nastran, I have to use a different operating system, a Linux server on my network that has the Nastran 2023.2, I think, is the version we want. So what we're going to do here is access a tool called the Remote Execution Web App. So let's go ahead and open that tool. Let's go ahead and do this. Let's go ahead and open and upload the bulk data files. We're going to send these files to that remote Linux machine, and we'll go ahead and run MSC Nastran. So you can see that this Linux system has Nastran 2024-2. And right now I ran Nastran. Let's go to the result files. Let's go ahead and do this. Let's download the F06 and the H5 file. So that would be these two files that we've downloaded from the Linux machine. Let's go ahead and download those to my local desktop. Okay, okay, perfect. So I do get results now. So if we look here at, say, the displacements, so every point on this graph is outputted for us. So here, you can imagine that every point here would be this value in this column. So 0.1418, 0.106. Now, what we want to do, we want to take the maximum value out of all of these points. So what we went ahead and did to the bulk data files, we configured this for Sol 200, and we use the DRESP1 entry. We said, hey, call out the acoustic pressure. So the response type is set to press, short for pressure. And we said, hey, take the maximum value out of each point on this graph, each point in this column. Find the max value. That's the value we want to track during the uncertainty quantification and the optimization under uncertainty. So now that we have the H5 file, we can start this exercise. So let's go to the machine learning web app, and let's go ahead and upload these bulk data files. So we'll go ahead and look here, and we want to go ahead and find the desvar entries. So here are the initial value fields, field 4 for the desvar entries. We'll go ahead and select those as uncertain variables for this exercise. Now, what about the responses? We are going to go ahead and select the H5 file. The H5 file is going to contain the maximum acoustic pressures and the mass of this acoustic box. So when you use this tool, you'll notice that this left-hand dataset box, it's too narrow for our liking. What you can use are these two buttons to resize the box. So here, let's go ahead and select the response type 2 dataset. So optimization response R type 2. And here you'll see that A1 and A2 correspond to these DRESP1 entries. So A1 is going to be the max or peak acoustic pressure for one of the nodes, and A2 is going to be the peak pressure for the second node. So here in A1 and A2, we'll go ahead and select this column, the response value. So 204 is the peak response for the first node, and 47.859, that's the peak for the second node. When we select these two responses, here on the right, we have response R1 and R2. So we're going to be tracking these peak responses, and they're now labeled R1 and R2. Now, what about the weight or the mass? We can go to the nodal grid weight dataset. And here we'll go ahead and select MX as the mass that we want to track. So that would be R3 here on the right. Now let's go and navigate to settings. Here, let's switch to Dakota. We are using Dakota to perform this robust design optimization. So we'll go ahead and we'll set the UQ method to sampling. And we'll go ahead and select the OUU approach to, here, let me look at my notes here. Surrogate-based OUU formulation 3. So this approach is explained in the presentation. I think while this is running, I'll explain what this approach is. For now, let's just go ahead and focus on filling out this optimization under uncertainty or robust design optimization. So for the uncertain variables, we're going to say that the standard deviation for the uncertain variables is as follows: 0.001. Let me make sure I supply that value. Now, the standard deviations are typically found from experiment. Either you've manufactured your structural or mechanical system multiple times, you measure what the standard deviation is for the thicknesses, or if somebody else, some other company manufactured this for you, they would have the standard deviation for the uncertain inputs. Now, here under optimization under uncertainty, we need to specify what the variables are. Here we are going to say that the means of the uncertain variables are going to be the optimization variables. Here for the lower and the upper bound, we're going to say the lower bound is equal to 0.001 and the upper bound is 1.0. So we're saying that the average thickness would vary between this lower and upper bound. And now let's go ahead and move on to the next page. And now let's go ahead and scroll to OUU constraints. Here you have the option of internally working with reliability indices or probabilities. Today, we want Dakota to generate probabilities for the response levels, or the lower and the upper bound we configure here. Now here we only want to assign a constraint to response R3, which is the mass constraint. We say that, hey, during this optimization under uncertainty or robust design optimization, make sure that the probability of exceeding this maximum mass of 2910 is at most 3%. So when you do this, it automatically creates a constraint column in this next table. Now, let me look at my notes and see if there's anything else we need to do here. And here in this table, the configure OUU constraints table, make sure there's nothing provided for response R1 and R2. If you look at the input box for both of these rows, you can see they are all blank. Again, we are not constraining the acoustic pressures. We are only constraining the mass, which is response R3. Now, in this next table, this is where you can configure the objective for the robust design optimization. Here, we can select the mean and standard deviation for response R1, and we'll repeat that for the mean and standard deviation for the second response R2. Here, we're saying, hey, take the total sum of all of these responses, take the sum of the products. So here, we're saying, take the sum of the product between R1 mean and the scale factor 1 plus the product of R1 standard deviation and 3 plus so on and so on. So here, what we've configured here in these input boxes and these scale factors, we've configured this objective, which would be here in the right hand side. Let me zoom in. So we've configured this objective here. You can see that, again, we're taking the total sum of all of these responses, and for each component, we're taking the product of that response, say the mean of R1 and the scale factor. And here in these input boxes, we've supplied what the scale factors are. Now, one quick comment about the scale factors. If for some reason you wanted to minus some of the values instead of summing them, you just have to use a negative scale factor. So here I've typed in -3. This is going to go ahead and do a minus operation, but here we want to take the sum, so all the scale factors are positive. Okay, then let me look here on my notes and see if we're ready to go on to the next step. Okay, now anytime you modify the sampling, or anytime you modify the UQ method or the OUU approach, this is going to load default settings for the method and the model keyword blocks. So here on the right is the equivalent Dakota input file. There are some modifications to some of these settings. So if we go to model, we want to configure the surrogate model that's used. Now, what's going to happen in a moment, I think this would be a good time to explain what's going to happen. we are going to build what's called a surrogate model. So that would be this here on the right. Instead of running Nastran maybe 10,000 times, 5,000 times, we are going to build a surrogate model that looks like the actual response surface. So here on the left is the true response surface for the acoustic pressures. This is for R1. We are going to build this approximate response surface using a Gaussian process regression method. So if we go back to the model section of this tool, we need to configure the surrogate model. If you look here, the surrogate model is configured to use a polynomial surrogate model, but this isn't going to work well for this very complex response surface. You can see that there's no quadratic or cubic equation that's going to help fit this model. So we are going to modify this. We're going to say, hey, use a more flexible surrogate model. Here we are going to be using the Gaussian process surrogate model. So let's go ahead and make sure I modified that. So here next you want to mark the checkbox for GP implementation. Now there are two different implementations, one provided by SurfPack and the other one provided by Dakota. I believe SurfPack is not configured on this desktop, so we'll go ahead and just use Dakota's implementation of the Gaussian process method. Now let's go ahead and modify another default setting. Let's go to the method section. Let's modify the number of Nastran runs that are used to train this model. Now you can see that under the DACE method, so let's go ahead and make sure it says DACE here. So this would be the method keyword block for DACE. Here, do not confuse this with this other UQ method, UQ and Optim. Look for this keyword block where the ID method is equal to DACE. Now here under samples, let's turn that on. Let's say run Nastran 40 times to build the surrogate model. And let's go ahead and select download. Now what I'm going to do is the following. I'm going to download the existing set of solution files. And what I'm going to do, I'm going to compare the known to work input file and the input file I created just now. So here on the left, let's go ahead and open the new input file. Let's go ahead and wait a moment for this to download. Okay, now we've downloaded the new directory, Nastran working directory. Let's go ahead and extract the contents of that zip file. Now, again, I want to compare this input file with a known working input file just to make sure I've done everything correctly and according to the procedure. So go ahead and compare these input files. Perfect, they're both the same, so we followed all the steps that we needed to. Now here at this point you would go ahead and click on start desktop application to start the optimization under uncertainty or the robust design optimization. Now what I'm going to do is this. I don't have the newest version of Nastran on this desktop, so I need to run to my other operating system and run the robust design optimization there. So let me pause the video here and do that. Okay, so I started the optimization under uncertainty on my Linux system. Here you can see it's running right now. So we'll just wait for that to go and do its thing. Now, while this is happening, it would be worth talking about what is going on in the background. So let me see if I can find another presentation here. So if you're interested in learning more about surrogate modeling using the Gaussian process regression method, there are a set of tutorials on Gaussian process regression. So let me see if I can find us a tutorial for that. Okay, perfect. So here, this is what's going on. Let me use this example to explain what's happening. So our acoustic box is in 2 dimensions. We're varying 2 thicknesses. Well, we went ahead and did it. We said run Nastran 40 times for different configurations of the thicknesses. Get the responses, get the acoustic pressures, and build a surrogate model. So here is an example of that procedure. Here we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We ran Nastran 10 times, and then we fit a function through those points. And then we run additional points. Maybe we run up to 40 points. So maybe our response function looks something like this. And this is what the contour looks like, at least for this response function. You can see here on the right that the points that are used are distributed across the design space. I think our range of values was 0.001 and 1. So we're probing the design space. We're collecting the acoustic pressures. So what you see on this slide, let's go back here. What you see on these graphs, you see the results of that training. So here we've ran Nastran 40 times. After we run Nastran 40 times, we construct the approximated response surface. So this is what it looks like. This is what the approximate surface is for R1. This is what the response surface looks like for R2. And here on the left are the true response surfaces, just to give you an idea of how close the approximate surfaces are to the true response surfaces. Now for R3 is the mass, so typically that's usually a plane. And here on the right is the approximated response surface for the mass. It's a plane. Good. So the approximation is good. Now let me take a moment to run to my Linux system and recover the result files. Actually, you can actually see me do that here. Let's go ahead and navigate to where I have the result files. So that would be here. So let's go ahead and do this. Here on the right is my Linux system. So let's go ahead and just copy everything here. We'll go ahead and just bring in everything that's new. And we'll do that here in the workspace D directory. Bring in everything that's new. Okay, now if I go ahead and click Start Desktop App, this should be able to open the result of the optimization under uncertainty. So let's go ahead and wait a moment. Okay, so when you, or after the optimization under uncertainty, you get all these pages that show you some results. Let's go ahead and maybe take a look at the results of the OUU, or robust under optimization. Now, if we look at the objective, remember that the objective was the sum of the mean plus 3 standard deviations for R1 plus the mean and 3 standard deviations of R2. We wanted to minimize that sum. If we look at the objective function, you can see that the total value at the beginning was 432, but then by the end of this OUU, it's reduced that sum to 227. That's indication that it successfully minimized that robust design optimization objective, the mean plus 3 standard deviations. Now, here are the normalized constraints. This is giving you an idea if you're violating or satisfying the constraint on the mass of the acoustic box. If it's positive, you're violating that constraint, but if it's negative or nearly 0, you're satisfying the constraint. Now here on this next table are the design variables. You can turn on either design variable, but here we're looking at all the design variables. You can see the change in the means of the thicknesses for the acoustic box. And everything that you see in these web pages are also available in the Dakota output file, so we navigate to workspace D and open the dakota.out file. Everything that Dakota was doing is logged here. So let's quickly go through this. If you look here, at the start of this whole procedure, Dakota has requested 40 samples. So it's created 40 different permutations or configurations of the design variables. And for each configuration, it's run Nastran. So here, this is the first configuration of variables x1 and x2. The blocking fork is where it runs Nastran, and then recovers the responses R1, R2, and R3. So these are the peak pressures and the mass. And then it moves on to run 2, run 3, and it repeats the process again and again. Run Nastran for this new set of variables, collect the responses, and repeat this 40 times. So if we go to run 40, at the end of run 40, it then starts to build the approximate models, which in this case are Gaussian process models. So here you get some information about the construction process for the models. And now in this next step, we run an uncertainty quantification. So, and the UQ method that we take is a sampling method. But here, instead of running Nastran 5,000 times, we run the surrogate model 5,000 times. Remember, the surrogate model is the approximation of the response surface, which is very cheap to run. It runs in milliseconds. So here what we do, instead of running Nastran 5,000 times, we run the approximate model 5,000 times. So here, this is the start of that UQ. We run Nastran 5,000 times. I think it's here. Nested model evaluation 3 results. And I imagine this goes up to 5,000. Here at this point, you see that there's some iteration between the optimizer and the UQ process. But at the very end, you get some feedback on the final results. Here it says function evaluation summary. Here it tells you that it's performed the evaluation of the black box function about 500,000 times. But this is not running Nastran 500,000 times. In the next row, it tells you that it's run Nastran 40 times to acquire the 40 responses, basically training data. It takes the training data, it builds the surrogate model or the approximate response surfaces. Then, anytime the optimizer needs new statistics for the mean standard deviations of the responses, it runs the surrogate model. So during the entire optimization process, it ran the approximate model more than 500,000 times. And this only took a few seconds. If you look here at the bottom left at the total wall clock, this took a little bit more than 2 minutes to run. If we were to run Nastran 500,000 times to perform the uncertainty quantification multiple times, this could have taken maybe more than an hour. But here it was really quick. We did it in less than 2 minutes. So here you see the best parameters, basically the variable values at the end. So if you zoom in at the very end here on the right, these variable values are the same ones that are being reported here. We see the new objective function at 227, which is the same objective that we saw here, 227.55. That's reported here. Okay, now one key thing about this. During the OUU, the robust design optimization, we use the approximate model to approximate the true response values. So there's a chance, or it's a fact that there is some error in this OUU. So now we have to confirm whether or not we satisfied the probability of failure constraint. Are we really less than a 5% of probability of failure? So in the next part of the tutorial, we go through this confirmation process. So here what we're going to do is the following. Oh, one quick note. Everything that you saw in the Dakota, or the last part of the Dakota output file, is also published in the Dakota results web app. So that's this web app here. You could turn on these additional columns and view some more information. Here you get the probability of failure is 0%. So there's a 0% chance that you exceed the value of 29100, which is the mass, the upper bound on the mass. There's a 0% chance. So the question is that true? Are we at 0%, or are we at 3%, or are we at 10% probability of failure? So that's where we come to the next part of the tutorial. We go through this confirmation process. So let's do this. Let's close all these windows. And let's go to the Dakota section. Let's go to the wizard. Let's go and change the OUU approach to selected OUU formulation 1. And let's go to method, and let's say that we at most want to run this for one design cycle. So what we do is we turn on the max function evaluations and we set that to 1. Here, let me look at my notes and make sure that's exactly what we want to do. So here, just bear with me while I look at this real quick. Okay, yeah, it looks like it's 1. So let's go back to the wizard and do this. Let's go to the configure OUU variables. And what we're going to do here is the following. Take the optimal values for the mean. So here for x1, we copy this value and we paste it here as the initial value, and we'll do that again for the second variable. So copy and paste. So what we want to do is the following. We want to run an uncertainty quantification one time to compute our objective and our constraint values. So that's what we're aiming for. And here, let me look at my notes just to make sure I'm doing this again. Okay, so we're doing sampling, nested OUU, configure OUU variables. Okay, now there's one other thing we want to do. Here, remember that for the optimization, we made the probability of failure more strict. We set 3% probability of failure. But now we want to know the true probability of failure, so we revert the value to 5% here. Okay, well, let me see and check if there's anything else we need to do here. So here it's telling me go to the method section. Right, and we already set this to 1. So now let's go ahead and download these bulk data files. And now, like before, I don't have Nastran 2023 on this desktop. So what I need to do is I need to run to my other Linux machine and start the procedure there. But before that, let me actually make sure that I've configured this properly. So here I have a known working input file. So let me compare this new input file with this known to work input file, just to make sure everything has been configured properly. So here we'll rename this working directory 1. Let's go ahead and compare. Okay, so there was a small difference. The difference is as follows. This time when I performed the OUU, the OUU solution that I got today was different than the other time when I was making this tutorial. So here, if you look at the initial point keyword, you'll notice that the initial values that I'm using before and after. So here on the right are the initial values I used maybe 4 or 6 weeks ago. So this was the solution for that OUU, or robust design optimization. Today, here on the left, we have a different solution for the OUU. Now, this should be expected. Just using a different operating system like Linux or Windows, that's enough to give you a different solution when it comes to dynamics responses. Today we're using acoustic pressures. It's a dynamics response that often will give you different solutions, optimal solutions, depending on the operating system, the version of Nastran. Even if you make one change to one of these other values, for example, suppose we change the starting mean. We made this maybe a 9 instead of 0.02. That's enough to give you a different optimal solution. But that's okay. What we want to do now is carry on with this confirmation. So we'll accept these initial values. We'll accept that this is where we want to perform the verification. So right now, let me take a moment to run to my Linux system, copy the files there, and start the OUU there. Okay, so now the verification process is happening on my other Linux system. So let's go ahead and navigate to that. So here you can see that verification is running. Now, one important detail I forgot to mention, in the Dakota section, make sure that the number of samples that are used are 50. So basically we're saying run Nastran 50 times, get the peak acoustic pressures, and then calculate the probability of failure of exceeding the mass constraint of 2910. So here, just make sure the samples is equal to 50. I think by default, sometimes it's set to 5,000. You do not want to run Nastran 5,000 times. It might take more than an hour. So let's go ahead and set that to 50. And now let's go ahead and talk about the final goal. So in a moment, we are going to create these plots. Now, let me use Excel to create these plots. I'm assuming that you're completely new to the world of statistics, uncertainty quantification, and optimization under uncertainty and robust design optimization. So one thing you'll need to do, you'll need to create these probability density function plots by hand. So I'll show you how to do that right now. So let's go ahead and do this for the first mean. Here, I think I'm ranging from 0 to 400 decibels, I believe. So we'll say that this is Ri. So this is either response 1 or 2. We'll say we'll go from 0 to 400 here. Let me make sure I'm on the right spot. Okay, so let's go ahead and navigate and make this 400. The windows you saw a moment ago, that was just the completion of the OUU. And then we'll say here the mean and standard deviation. We'll say this is the initial or PDF initial and then PDF final. And here we'll use one of Excel's built-in functions, norm.dist. Here we'll say that the mean is this, or first we need to pick a point. So let me delete that. We'll say compute this for 0. Then we supply the mean and the standard deviation. And we'll say that we don't want cumulative values. Cumulative means that you're calculating the area under the PDF plot. But I'll say false. Don't give me the area, just give me the PDF values. And now you'll notice that it's saying that we didn't supply a mean and standard deviation. So let's go ahead and type in values for that. And here what it's doing, it's changing the values for the mean and standard deviation, which is not what we want. So let's go ahead and use the $sign to fix those values. And then we'll go ahead and do this for the second column. So let's go ahead and move those here and here. And now if I double click this and this, it should give me good values. So if we go here, perfect. Okay, now let's go ahead and take the initial mean for the first response and the standard deviation. So we're building a PDF plot for response R1. So these values that I'm using now, these are the mean and standard deviation of the original design model. So let me do this. Let me go to my Linux system and just copy over the files. So let's go ahead and do that now. Let's go in here and do the same. So if we look in the Dakota out file, here at the start of the Dakota run, you see that it's requested samples 50 times, and now it's running the first sample. Here are the values for X1 and X2 for sample 1. Here it's running Nastran. Then we get the peak pressures on the mass, and it repeats this process 50 times. And then at the very end, it runs the optimization procedure, but since we use at most one function evaluation, it terminates after one. We wanted this to terminate after one job or one run, one function evaluation, one design cycle, if you will, of the OUU, because we just wanted to know what the objective value and the probability of failure. And here we see what those values are. Let's go ahead and see if we can find some information here. Right. So here in this next section, we get the mean and standard deviation for response R1 and R2. We also get the corresponding probability of failure for the mass. These are the mean and standard deviations I want to use when I build the new plots. Now, keep in mind that since we had a different solution here, it might be worth doing this. Let me add a new row here. So we'll say add a row here below. And maybe we'll join these rows. So let's see if there's a way I can join or merge. If I go to design or layout. Okay, maybe there is no. Let's see if we can join this. That's okay. So here, let me label this. So this would be the values for this point. So let's go ahead and type in that here. Let's do this. Okay, so then for R1 and R2, what are the mean and standard deviation? So that would be these values. And let's just go ahead and copy and paste the mean for R2. And we'll do that again for the standard deviations for R1 and R2. And now that we have this data, we can go in and bring this data over to my Excel spreadsheet here. So let's do that right now. So here in column 1 is going to be the initial mean and standard deviation for response R1. So response R1. And then we'll go ahead and copy the mean and standard deviation for OUU solution 1. So OUU solution 2 is going to be the solution we got today just now. So I want to show you the different results that we would get. So here, let's go ahead and copy the mean and standard deviation for the OUU solution 1. Now, if you get a different solution, that's perfectly okay. The important thing is that you're able to narrow, you're able to decrease the spread of the probability density functions. That's the whole goal in robust design optimization. So here, let's go ahead and build this second plot. So PDF final solution 2. And let's go ahead and bring that down here. I'll just make sure I did this correctly. Okay, I'm using the wrong value here. So it's always good to double check and make sure you've selected the values that you need. Okay, let's go ahead and select these cells and create our PDF. So we go to insert. Okay, perfect. So let's go ahead and look at this PDF, and let's go ahead and move our legend so it's on the right. So here's a look at the original PDF here in blue. So you can see that if we took the original thickness values and we went ahead and manufactured this acoustic box, you can see that the peak pressure, the sound an individual hears at those different node locations, you can see the variability in the response. So if the thickness is changed just a small amount, the response an individual here would vary significantly. So here the average was about 210 decibels. It's very easy for an individual to hear a pressure of about, I don't know, here, let's go ahead and look, 230 decibels. I think the acoustic pressures are being measured in decibels in this case. Now, here you can see that the plot is very rough. You can see this very sharp corner peak. That's because I didn't use a lot of points. So one other thing we can do here, we could say instead of using 10, use a 1, increments of 1 rather. So here we go, and we drag this down. Let's do that. Let's go and drag this to 400. Let's go ahead and delete some of these rows. We only need up to 400. And we'll go ahead and move this over. And then this plot has to be updated, so it selects all 400 values. So now that we're using more points, the PDF plot should be a lot smoother. So let's go ahead and take a look at that. So let's go ahead and zoom in. Right, so now you can see it's a lot smoother. Now, you notice one thing about these new PDF plots. They are more narrow. So before, small changes to the thicknesses were significantly changing the acoustic pressure that you get. Here you can see that now small changes in the thickness won't necessarily lead to a bigger change in the acoustic pressure. The standard deviations here of the new PDFs are a lot more narrow. Here in orange is the PDF that's documented in the tutorial. But today when we went ahead and configured this optimization, we got a different solution, which is the solution in orange, or gray, sorry. So here in gray, we're still able to achieve the objective. We want to narrow the PDF distribution. What we did here on this page was done for response R1. What about the second response? So let's go ahead and create a duplicate of this Excel spreadsheet, and let's call this R2. And here we'll say rename response R2 here at the bottom. And now, like before, let's go ahead and modify the mean and standard deviation. So it's using the mean and standard deviation for response R2. So let's go ahead and update these values here. So for the initial mean and standard deviation, let's go ahead and copy the values from the table in the PowerPoint. Let's paste that here. And let me go ahead and do that. Now, while I'm doing this copying, let me remind you that when you go through this exercise, and if you get different answers, that's okay. That's expected. Being off by 1 decimal point, changing one other setting, using Linux versus Windows, using a different version of Nastran, that's enough to give you a different solution, and that's perfectly fine. what you want to make sure that you successfully reduce the distribution of your PDF. So here, let me just make sure I've typed in these values properly. I notice these values are in scientific notation. Let me change those to just plain old numbers. Here, there might be a problem with this one. Okay, here we go. So 49, 14, 32, 5, 31, and 5. Okay, perfect. Now you'll notice that the range of these values, it's a little different. I see these are going from 0 to 100. So maybe let's go ahead and adjust the values that are selected for this plot. So let's go ahead and move this to 100. So like I was saying before, if you get different values, that's perfectly fine. What's important is that you're able to reduce the spread of your PDFs. And here you can see what that looks like. Here in blue is the original probability density function for response to R2. So it's the spread of the acoustic pressure. Small changes in the thickness led to significant changes in the probable acoustic pressure that you get. So you can imagine that if we manufacture this acoustic box 1,000,000 times, this is the spread of the acoustic pressures an individual would hear. Now here in orange and gray are the new PDFs that we got after the optimization. You can see that the spread has been narrowed. Sometimes you refer to this new design as more robust. It's the probable output would be less different for this optimal set of design variables. So here in orange is the solution that we got when the tutorial was made. But again, because of subtle changes in the operating system or the version of Nastran, you might get a slightly different answer, and that's perfectly fine. The important part is that you're able to narrow the standard deviation of your responses. You're able to narrow the PDF plot like you see here on the screen. Now let's go ahead and jump back to the PowerPoint presentation, and let's go ahead and see if there's anything else here. Right, so let me run this one time. After the OUU, it'll go ahead and open all the result pages. Here, the last thing I want to show you is the probability of failure for the mass. Remember, we wanted to make sure that the mass doesn't exceed a certain weight, and we want to see what the actual probability of failure is. Recall that in the second part, we ran Nastran 50 times to confirm the true probabilities. So here, if you look at the constraints table, we see that the probability that we exceed 2,900 units of mass, the probability is now 0. I believe in part A, the probability of failure was 0%, and that was based on the approximated response surface. In part B, we ran Nastran 50 times, and we generated the actual probability of failure. The actual probability of failure was 0%, which is less than the 5% that we wanted. So great, we're satisfying the one constraint we had. Now, I believe that's the end of this one tutorial. Now, I know this was a lot. There are a lot of steps involved, but I wanted to make this example a little complicated because when you go ahead and perform your optimization under uncertainty, it will also be complicated. But hopefully you found that in this tutorial that it's possible. It's possible to do all the steps. It's possible to achieve the objective, which was to reduce the spread of the probability density functions, and that was the whole goal in robust design optimization. Now, here at the bottom, I am leaving you with my contact email. If you have a question, if you have ideas on how to improve this tutorial, if you have questions, comments, and any other feedback, you're always welcome to contact me at this email address. So with that, that's the end of the tutorial, and thank you for watching.